Hello, everyone. Welcome to this technical session on the last day of the Word for Women in Science. Today, we are here and we welcome you to listen to the presentation on innovations and agriculture and sustainability. This is one of the last panels of the last day of this festival, and we welcome our three speakers. According to the problems, we should have had more presentations today, and we hope other speakers are going to join during this 1 hour and a half of discussion. We welcome everyone to ask our questions using the Q&A function here on Zoom. And with no further ado, I would like to start with the first presentation by the master students, Maria Tomás Costa. She's a researcher in the Bazaruto Center for Scientific Studies in Mozambique. And I welcome her to share her presentation, to share her screen. And I wish everyone a good festival, a good session. So the floor is yours. We cannot hear you? Okay.
Yeah. Can
Perfect.
everyone hear? Maybe I can do a little bit of presentation to see my face. Hi, everyone.
That's great.
Yeah. First, I would like to thank this opportunity to be here and to do the presentation of my research. This was a part of my master thesis at Gorongosa National Park. And it's a pleasure to be here and to do the presentation for you guys. Sorry. I'm gonna share again. Okay. My research was about soil carbon stock in coffee agroforest system. And this has a way or a strategy to mitigate the climate change in Mozambique center of Sofala province. In the last decades, we have faced so many problems concerning to climate change, and many of these problems, the main driver is a human or anthropogenic activities. And the most of them is a deforestation, where most of the people change the land use to practice a lot of activities. And at Gorongosa National Park, as we can see in this map, since from 1977 to 2019, we lost 37.8% of the forest. As we can see here, the purple is the color of the forest lost, and the green is the forest remain in this ecosystem. And not only the forest was lost, but the biodiversity, the ecosystem function, and so many things was lost in this region. That's why the park started a restoration project, planting coffee as a way to mitigate climate change, restore the biodiversity, and to give the community around the mountain the opportunity to change the way they practice the agriculture. So the main objective of this research was to study the contribution of coffee agroforest system on Mount Gorongosa to soil carbon storage. For that, we choose 5 different start areas or 5 different land use One was a mature forest fragment. The other one was a fragment of regenerating forest, and the agricultural land. But this land was followed close to 3 years, and 2 years coffee agroforest system and a 7-year coffee agroforest system to try to see how was the dynamic of the carbon in these 5 land use from different perspectives. And we use a common method used where we collected 10 sample sites. We collected a soil in 10 sampling site were randomly selected in each land use type. And those sites were separated by 20 meters or more. And in each site, we collected a soil close to 1,500 grams, where we collected in 2 depths, to 0 to 15 centimeters and 15 to 30 centimeters. All this soil were taken to the lab where we process it, we sieve, we dried, and then we prepared to take to the lab where we quantify the different components we wanted to determine. The fine hair fraction content, as well as the soil and fine hair bulk density, were determined in the both depths, but the total organic carbon was determining using the common method, the dry combustion, and the fine hair fraction bulk densities and the volumetric percentage of the fine hair fraction were used to calculate soil organic carbon across the depth 0 to 30, not 0 to 50 and 50 to 30. We just combined the depth. And we determine the microbial biomass carbon and microbial biomass nitrogen using the common method fumigation extraction. And the soil respiration were collected, were measured using the Isomer method, but we changed this method according to the material we had in the lab. And we also determined the labeled carbon. And for the data analysis, we did a 2-way ANOVA for the total organic carbon content, and ANOVA, the 1-way ANOVA for soil carbon stocks, and for microbial biomass carbon, microbial biomass nitrogen, labeled carbon, and the soil respiration, we did ANCOVA. And before the analysis, we just test the normality and the homogeneity in the variables. And the variables without normality, we just convert using the log. And after that, we just did the toolkit test where we performed following the general linear model to determine the difference between the land use based on alpha of 0.05. And the best fit models we produced after the general linear model, we selected based on the ICER's course, and we removing the non-significant variables. And here we have the first results. This is the table showing which variables were the part of the best fit model. For the total organic carbon, we saw their land use type and depth, they had effects on these variables, where in the first step, we have more content of total organic carbon, and in the second step, we have low concentration of total organic carbon. And for microbial biomass, both just only land use have effect on it. And for the soil respiration too, we have a significant effect only land use. But for labeled carbon, we have significant effect of land use and carbon stocks. And we saw that when the labeled carbon increase, the carbon stocks to increase in different land use. And here we can see two graphs. where I show the total carbon and the carbon stocks. As I was saying, we can see the first graphs that the total organic carbon decrease with the depth. And both coffee agroforest system have the low concentration of total organic carbon in both depths. And these suggest that maybe we are not having input of organic matter in the topsoil. Oh, sorry, we are having input in the topsoil and not many input in the subsoil from 15 to 30 centimeters. And the second graph shows us the carbon stocks in different land use. And we can see there is a significant difference between the land use. And as we hypothesizes, because many studies show that coffee agroforest system tend to have carbon stocks close to native forest, and we expected to see these too. And our results show that both coffee agroforest systems have a carbon stock close to native forest, but we didn't expect to see a follow-up agriculture land having a higher concentration of carbon stock, because this is a land used with disturbance. But as we can see, we saw in our field that in the agricultural land, we have so many grass and a presence of cattle. And these two variables can have effect on a quantity of carbon stocks. But this carbon stock mostly is labeled, what shows us that it is not viable for the long use term or to use as a reserve of carbons to mitigate the climate change. And here we have a result of microbial biomass, carbon and nitrogen. And we can see that in both graphs, the 7 years agroforest system have a different quantity comparing to the other land use. And the microbial biomass mostly have seen that is in a land use with disturbance, we have a higher quantity of microbial biomass, but our result doesn't follow this pattern. What shows us that disturbance per se doesn't drive the quantity of microbial biomass. What is have to be done is to monitoring the microbial biomass before and after disturbance to see how these have effect on land use change during the more of the 1 years or 2 or 3 years, how can be related to land use change. And here we show the results of soil respiration and labile carbon. And soil respiration was low in both coffee agroforest system, and we can relate it with the quantity of microbial biomass because the microbial biomass drive the soil respiration, the microbial respiration. And we can relate it too with labile carbon, knowing that labile carbon is the first carbon that microbial use for the respiration. And that these labile carbon have a low residence time comparing to the other carbon that is in the soil. So, and we can relate these results with the presence of trees in our coffee agroforest system. Most of the studies show that the presence of native trees, fruit trees, and crops drive the change of microclimate in the coffee agroforest system, and we can relate our results with this suggestion of so many studies and show that using coffee agroforest system is the good way to reduce the soil respiration or to reduce the release of carbon dioxide to the atmosphere. And as a way for conclusion and suggestion, we found that coffee agroforest systems store organic carbon at level comparably to mature forest fragment and regenerating forest fragment. Although we also found that higher carbon stocks in agricultural land use and more CO2 was released from fallow agricultural land comparing to the coffee agroforest system. And in overall, our results can suggest that coffee agroforest systems are able to store organic carbon and with effective management may play a role in mitigating greenhouse climate emission and reduce the pressure of climate change. And for better understanding for this role of coffee agroforest system, especially in Gorongosa National Park, is necessary to do a long-term studies where we can try to trace all process, because the process in the soil take a lot of the time. So this is not a conclusion to tell something to have a strategy in our coffee agroforest system land. And I would like to thank the Gorongosa National Park and the universities that work with me in the lab and to do the analysis from the soil. And thank you, as we say here in my province, Kanimambo.
Thank you. That was inspiring. Actually, this presentation quickly inspired really a question from Acacio. He thanks you, and if you would like to answer now, is asking, it's a very good job. I would like to know if the park has a financial mechanism to use the carbon stocks in benefit to communities. It's a very local focused question.
Oh, yes, the park have a, thank you, Akashi, for the question. And the park have a financial mechanism to use to a carbon stock, but this was the first study about carbon in the park. So now we are not able to do the to be a part of the Red March or Red Plus or the other program to sell the carbon, because this was the first study. But now we have other students doing their research, so we can have more data able to be a part of main programs using carbon stocks as a benefit to the communities. This was the first one, and this was the first data available in the park. But now we have more data, because when I did the start, the coffee had 7 years, but now I think the coffee plantation have 10 years or 11 years, so we can conclude more about the carbon stock in different land use.
Thank you so much. I welcome everybody to add their questions if they have some. But in the meantime, I would move on to the next speaker. And I'm welcoming Mr. Oleka. Mr. John Oleka is manager at Nigeria's Social Insurance Trust Fund. And I welcome him to, I leave the floor to him to introduce himself, and I'm going to share his presentation for you all.
Good afternoon, all. Yes, my name is Oleka John. I'm a PhD student of Electrochemical Technology from the Africa Center of Excellence for Future Energy and Electrochemical Systems, Federal University of Technology for Owerri, Nigeria. I'm also a manager, health, safety, and environment at the Nigeria Social Insurance Trust Fund, NSIT. I will be speaking.
Thank you. I would welcome you to, I'm sorry, Mr. Leka, if you could approach the mic better, it would be great. Thank you.
Okay. Okay. Can you hear me now? Hello?
Yes, I can hear you better.
Okay, okay, that's good. Okay, so I will be speaking on the subject full spectrum driven photocatalytic hydrogen production using ion doped titanium dioxide and zirconium sulfide. And this is a presentation to the 8th World Forum for Women in Science 2024, holding in Italy. As earlier mentioned, I'm Oleka Ikechukwu. Background. The ability to generate clean and renewable energy from sun offers tremendous potential, especially as regards to reduction of greenhouse gases and the mitigation of climate change and its impact on the environment. The problem here is that most often we use fossil fuel to generate energy and electricity. And this fossil fuel produces carbon dioxide, which is a greenhouse gas. And as a greenhouse gas, this gas, together with other greenhouse gases, they form envelope to the lower Earth atmosphere, that's the troposphere, wherein the solar radiation penetrates and passes through the envelope via the shortwave radiation. But the long wave radiation that hits the Earth atmosphere, returning back
I think I lost Mr. Oleka. I don't know if the other speakers can hear him.
No, dear Celeste, we cannot hear.
Yeah, I see he left the room. Maybe he has some connection problem. So I'll stop sharing his presentation. And I welcome also the audience to tell us if they were able to catch up with it. Mr. Oleka, can you hear us?
Hello, can you hear me now?
Yes,
Hello?
I can hear you better,
Yes,
actually.
I can hear you better, actually.
Oh, sorry, it was network. I'm sorry. So thank God. Okay, as I
Okay.
was
So are you
speaking before,
able to continue?
Yes, please, we can continue now. Okay, please, next slide, please. Next slide, please. Okay, so I said that the ability to generate clean and renewable energy from sunlight offers a tremendous potential to reduce greenhouse gas emission and mitigate environmental impacts of the climate. We use fossil fuel to generate energy and electricity. And one of the end product of this activity is what we call emission of carbon dioxide into the environment. And this carbon dioxide, alongside with other greenhouse gases, they form a
blankets in the lower part of the Earth atmosphere, wherein they allow the penetration of solar radiation in the form of shortwave radiation from the sun. And when this radiation hits the Earth atmosphere, it returns in the form of a long wave radiation. And as such, are being blanketed by these greenhouse gases, including carbon dioxide, which is the chief among them all. And the consequences are what we see as the impact of climate change. Therefore, photocatalytic hydrogen production is a sustainable approach that utilizes semiconductors materials to convert solar energy into hydrogen through water splitting. A typical illustration of what we are talking about is the figure 1 on the background. Now, you can see there is solar radiation, there is water, and there's photocatalyst. And this is all that is required, and hydrogen will be produced. And we say this is sustainable because it is available, the resources is available for the present generation, and we are sure of its availability as well for the future generation. It does not deplete, unlike fossil fuel that depletes. Now, titanium dioxide is a widely studied photocatalyst, but its band gap restricts its ability to utilize visible and near-infrared light, limiting its overall efficiency for solar-driven hydrogen evolution. What we are saying is that, yes, is a traditional photocatalyst, but that notwithstanding, it has a limitation. And one of the limitations is that its band gap is a bit wider. And because of this band gap, it can only utilize solar radiation within the ultraviolet region of the spectrum. So we intend to a kind of optimize, we tend to extend the absorption of titanium dioxide, not only to absorb within the ultraviolet radiation, but also to absorb within the visible and near infrared in order to maximize its efficiency, especially as regards to solar-driven hydrogen evolution. Now, a typical example of the process of water splitting is illustrated in page 3 of my slide. Here we have light irradiation, and when light hits the material, mainly the photocatalyst, there is a conduction band and there is valence band. Depending on the band gap of the material in question, there will be electron hole generation once there is solar light irradiation on the surface of the material. And when these electron holes are generated, you'll notice there will be electron hole separation. And depending on the quality of material used, there will be also electron hole transportation to the surface of the material. Oxidation reaction also occur, and also reduction reaction also occur. Then most importantly, there will also be a bulk recombination of degenerated hole electrons. And this is also a function of the material being used. So when a material that is not that good, just like the one we mentioned, titanium dioxide is used, there is tendency of the electron hole generated being returned, being recombined both in the material and also at the surface of the material. Now, the research design. The research design is developed for experimental and also for computational design and approach. For experimental, the material we need is a high purity and analytic reagent, and materials need to be prepared. We synthesize also the semiconductor or photocatalyst. We also intend to characterize the material we synthesize just to make sure that the material we synthesize is actually a photocatalyst. And when this is ascertained, the next we are to do is to carry out a photocatalytic study of the same material using using G2V solar stimulator. It provides irradiation, that's artificial radiation in the laboratory for the process. Then do have our data processing, presentation and analysis. And before the data processing, while the experimental is going on, there is also need for computational analysis. As a matter of fact, that is the first objective of the work. We want to use the BioVia material lab to optimize the sample materials in the lab, optimize them, get the structures, and study them before entering the lab proper. Now, the combination of what we have done in the computational modeling and the experimental modeling will be analyzed as a data and presented for analysis and interpreted, then a conclusion is achieved. Now, it's a work in progress. We just started as we speak at the moment. We are just at the first objective, which have to do with the computational analysis, computational modeling of the samples. As I said earlier, we are using the BioVia Material Studio 2020. Now we've been able to optimize zirconium sulfide using CASTEP, and this we are able to get a structure of the substance. We're also able to have the supercell of the same compound or the same semiconductor. And as you can see, figure 4.0 is the normal structure of the zirconium sulfide, while figure 5 is the supercell of the same semiconductor, that's the zirconium sulfide. We are also able to run the density of states of the same semiconductor using CASTEP. So you can see the presentation of the energy, that the total energy in the form of a graph, in the form of electron volts, as presented, I think towards the right hand of the slide. We're also able to do the band structure, where we have the band energy calculated. We were also able to do the optimization conveyance for the same structure, and not just for zirconium sulfide. We were also able to do that of titanium dioxide using CASTEP also. Is figure 6 is an illustration of the structure of anatase titanium dioxide. Then we were also able to run the geometric optimization of the same structure. We were also succeeded in doing the CASTEP optimization conveyance for the same titanium dioxide using the Material Studio. We also went further to carry out the doping of titanium dioxide at titanium with ion 0.5 weight percentage, just as it's required in Material Studio. Before we can calculate this, we have to convert from weight percentage to atomic percentage. And this has been successfully carried out. And the structure is also displayed here in figure 7. This is where we are at the moment. This is a work in progress. And I believe if opportunity can be given during the, what's it called, the 9th section of this very conference, I will appreciate if opportunity can be given to share other findings from this work. Now, the project outcome and impact. Now, the project outcome simply is for hydrogen production efficiency. And the impact of this project will include, not limited to, reduction of carbon dioxide emission. There will be also cost reduction in green hydrogen production. And we're also expecting a diversification of energy sources, not just limited to what we have at the moment. At the end of this project, a new other source of energy will be communicated. also transfer to other application. Example, this same photocatalyst can be used in wastewater treatment and other application. So it's not just being used for energy and the reduction of carbon dioxide. It can also be applied in wastewater treatment, and also is a contribution to the sustainable development goals. So these are the project impact. And it's also important for us to highlight here that this project will impact positively on some sustainable development goal, precisely the SDG goal 7, which centers on affordable and clean energy. It will also impact positively on that of SDG goal 13, which have to do with the climate action, especially as regards to carbon dioxide emission elimination or reduction. And also it will impact on the SDG goal 6, which have to do with clean water and sanitation, and also impact on SDG goal 9, which have to do with innovation in technology. And I like at this point in time to send my acknowledgements to the organizers of this conference for this privilege. And also I want to especially appreciate my supervisor, Professor Emeka E. Oguzie, who is also the center leader at the ACA Fuels FUTO. And also my special thanks goes to World Bank, funded the Second Africa Higher Education Center of Excellence for Development Impact as a ACA Impact. And at this point, I'd like to make it known to the conference that at ACA Fuel, we promote inclusion of women in science, technology, engineering, mathematics, plus energy through postgraduate training. And for more information regarding the activities of the center, please feel free to go to our website, www.acafuels-futo.org. And these are my contacts for future communications. You can reach me on any of the contacts as displayed on the screen. And I would like to say once again, thank you for the privilege and for this opportunity.
Thank you, and my apologies. There's echo in my voice. I hope you can hear me well.
Yeah, I can hear you.
I wanted to make my apologies because I know that the screen was frozen while I was speaking, so I hope it didn't ruin your presentation.
That's okay.
And before moving on, since we have no questions, but I welcome everybody to ask them to Circle. I would like to ask you what's the role of the World Bank project for research. If you'd like to like more in it, because that's interesting.
I didn't get your question very well.
So you showed that you have to thank the World Bank project for the support. In what way it was involved? In what way it STEM research?
Okay, thank you very much. The program I'm doing is a sponsored program. As a matter of fact, the ACA Fuel is a center in Futo that is being sponsored by World Bank. And this is the Second African Higher Education Center of Excellency for Development Impact. And as a student, I'm under scholarship. World Bank is taking care of everything about my lab work, and not just my lab work. World Bank is also taking care of some percentage of my tuition fee. And as I mentioned earlier, the center is promoting inclusion of women in STEM plus energy. I'm not enjoying 100% of the tuition, maybe because I'm working, We have other students from other parts of African countries, precisely maybe Cameroon, Togo, and all the rest of them. The center is, these students are in the center tuition free, 100%, and the sponsorship covered everything, including monthly stipends given to them and accommodation at the center for the duration of their research work. And for the women among us is 100%. So it's a well-sponsored program. I appreciate them for that. And I urge if this can be extended and for other beneficiaries in the future.
Thank you so much. From the audience also, thank you. Thank you. And it looks like a very important support for earlier, but also research dealing with materials and energies, and specifically targeting specific challenges of each context, as also Maria Tomás with their work in Mozambique. And for now, there's no question. I would like to give the floor to Professor Nun from the University of Sindh in Pakistan. I'd let the floor to you for your own presentation, and thanks again.
Thank you very much, Celeste. Can you hear me?
We can, yeah.
Yes, that's good. Then I'm going to share my screen. Is my screen going good?
Yes, we can see it zoomed in. Perfect. Thank you.
Oh, all right. Thank you. And first of all, I would like to thank Women in Science Without Borders and Traces&Dreams and the people over there. They are doing a great job. I enjoyed this conference very much. And I congratulate here because I am the last speaker, so I can say that this conference was a great success. So I would like to congratulate the team. And I am Professor Dr. Najma Memon from University of Sindh, Jamshoro, Pakistan. And today I'll be talking on the topic that is waste to resource, developing a textile binder from banana pseudostem fiber. And my work falls on the SDG 12, that is responsible consumption and production. So I would like to talk a little bit about myself, that I'm an academic researcher. And here is my profile, that I have published over 131 publications over my career span of 23 years, including books and book chapters. I have supervised 17 PhD, 20 master's students, presented and organized various events. By profession, I am analytical chemist, and I do research and teaching in analytical and food chemistry. But later, you know that during the research career, you have different lines of the research. So I had a project that says empowering Pakistani women through translational research in sciences, that was waste to energy conversion and water purification technology development. And this project was all about, you know, working on different materials. So this project changed our, opened a new stream of research in my group. And we started working on different kind of materials. And we focused on the conversion of waste into different valuable products. And we prepare materials that should be fit for purpose. For example, we developed certain sustainable and scalable antiviral fabric coatings during COVID times. So our focus of research is, one of the line is like materials preparation. And I also remained the editor of Pakistan Journal of Analytical Environmental Chemistry for 8 years. And later now I've joined the same journal as a senior editor. And I'm also associate editor in Frontiers in Materials. So this is just little portfolio, and I can be found on Google Scholar or on different research websites if someone is interested. So now I'll be talking about my topic, that is to convert the banana waste into some valuable products. So since we are talking about the banana, so we'll say that you can see here that the banana is produced worldwide And you can see here that India and China is producing over 100 million tons of banana. So there is a huge production of banana, and it is produced worldwide in over 120 countries. And in Pakistan, it is grown on 34,800 hectares with production of 1.97 million tons. So in Pakistan, there are different varieties, but Pakistan mainly focus on the Cavendish dwarf variety. This 95% of land is cultivated with this variety, and some of the land is also using different variety, that is William hybrid. So these are a few of the varieties that are produced worldwide, but Pakistan is producing Cavendish bananas. When we're talking about the banana fields, so you can see here that the banana fruit is a little part of the whole plant. It has got leaves, pseudostem, bunch stalk, and buds and root system. So once these banana fruit is removed, whole this plant goes into waste after a few crops. So there is a huge problem about the banana waste. Like after harvesting, almost 60% of the bananas biomass is left at waste. And you can see here the major fraction of banana waste, besides the leaves and the peels of the banana, is the pseudostems. So if we see that pseudostem is this part of the banana. So other researchers have also found the uses of banana pseudostem. So if we cut the banana pseudostem into different sections, cross sections, you can see here that it has a thread-like, fiber-like structure like here. So in textile industry, now there is great interest in producing banana fiber. This is just thread, this fiber that's extracted from banana. And this is very useful in textile, and they are producing the different kinds of products from it. However, after extracting this fiber, you can see here that there is this solid mass that is the secondary waste that is generated from the banana fiber industry. And there is an issue that for the survival of the banana fiber industry, that even if they are tackling the waste, but is still if they can utilize, create value-added products from other secondary waste, then this will add into their businesses and the sustainability of the banana fiber industry. So we were approached by the banana fiber industry to tackle this issue of secondary waste and to create something, a value-added product that could be useful once again in the textile industry. So our objectives was to produce some product that is that could be used into the textile industry. So we planned on the basis of literature that we can produce the binder. Binders are used in pigment dyeing for the textile products, dyeing of textile products. So we plan to have a binder from this secondary waste, and then we plan to characterize that how does banana pseudostem, the powder or the banana pseudostem waste looks like. And we also plan to characterize the banana. And then after having the binder, we apply this binder to the textile dyeing process to check the feasibility of this applicability of the binder into the textile dyeing process. So to produce the binder, we collected these pseudostems from the fields, cut into the small pieces and dried and then grind to the fine powder. And then we did some chemical treatments, simple enough to be carried out into the industry. We added 10% liquid ammonia, 100 ml to 1.5 grams of banana pseudostem powder, heated it, and then after digestion, we acidified with sulfuric acid, and then simply this resulted into a gluey mass that we termed it as a BPW binder, obtained from the banana pseudostem fiber and used it for the dyeing process. So since this is the binder that is used in the pigment dyeing process, so we adopt the process of the that's commercially used into the textile industry. We mix the binder with the pigment, dilute it, And then this solution was used as for the dyeing purposes. And to compare the efficiency of the pipette binder, we used commercially available binder that is normally used for the pigment dyeing process, that is alizarin binder, and we used the same process. So both these solutions were then tested for the dyeing purposes. So this is the process that we used for the dyeing, that this was dipped through the machine that was commercially available to the textile department of another university. And we dyed and we cured it in 120 degrees centigrade in an oven. And then we tested the feasibility of using this binder using various test parameters that are applied into the textile industry. So the parameters that we tested against this fabric that was dyed with red dye and using the binder that we developed. So we did curing test. Curing test is important whether heating is necessary or not. We also did the washing fastness, because once fabric is dyed, it has to show some good washing fastness. So we used ISO certified method to test it. We tested for the tensile strength, we tested for the stiffness, and we used two different kind of fabrics, that is cotton and polyester cotton fabric that is most commonly used. So it happens that sometimes the fabric becomes stiff and sometimes becomes softer. So we tested for the stiffness, we tested for the light fastness. We used blue wool scale for the light fastness. And this was the test procedure for the blue wool standard. And let us see what happened to this hypothesis. So as I already mentioned, that this solid powder was converted to a gluey brown solution that we termed it PVW binder. So the binder now is into the liquid state. We dried the binder and we took the FTIR spectra of the pseudo-stem fiber. This shows the red line. And we also tested the dried PVW binder. And you can see here that the two FTIR spectra are significantly different. And you can see here that there is OH stretch here. And but in case of pseudo-stem binder, there is a broad band that says that there is NH and OH group overlap. And this tells us that because we used ammonia for the dissolution, so there is some ammonium salt formation during the process. And also the other, the aromatic ring, because there is lignin present into the pseudo-stem fiber present, that shows various carbon-oxygen double bonds and carbon-oxygen double bonds. However, the intensity of the FTI peaks were increased. And I believe that this is due to the unfolding or realization of the tightened structure that was for the pseudo-stem fiber, which is relaxed now, and now binder has loosened the structure of the lignin and hydrolyzed cellulose, so it has more excess flexibility towards IR absorption. So the intensity of the absorption rate was increased, and this shows that the material was successfully converted to some other material that we term as the binder. We also did the surface morphology of the dry binder. We can see here that at the 50 micrometer scale and the 4 micrometer scale, this is the typical structure for the gums. When we dry the gummy material, we observe these kind of structures, this continuity and wrinkled surfaces. But when we zoom in to the nanometer scale, we can see here the crystals. And I believe that these crystals are maybe due to the ammonium sulfate, because we use the ammonia solution for the digestion purposes for the pseudo-stem biomass, and then we use sulfuric acid to neutralize. So probably there are ammonium sulfate crystals formed. So this also shows that the salts are deposited onto these structures. And then we apply this this binder into the dyeing process, and then we once again characterize the fabric. We use the cotton fabric and PC fabric, and we compare the surfaces of the commercial binder with our prepared binder, and we can see here that this binder onto the cotton surface has very fine pigment, very evenly distributed onto the surface, and likewise the similar results were also seen for the polyester cotton fabric. So we did not see any significant difference between the commercially available binder and the this green biomass-based binder for on the two type of fabrics. So this gives clue that this binder is very good for the coating purposes or using for the pigment dyeing in textile process. And these are very common tests that are used for to assess the efficiency of the binder. So we test for the washing fastness, and you can see here that this BPW binder and commercial binder has the same results. So these are very, very nice results and very comparable data. And washing fastness was also assessed on the gravure scale, and the 5 is considered the best. So in most of the cases, we got the 4 to 5 in case of cotton. However, for PC fabric, we got the value of 4, but still, these are very good results. And also, we tested the tensile strength. So we can see here that for PC fabric, the green binder has provide more strength to the fabric, PC fabric. However, is compared to the synthetic binder, and the tensile strength was similar for the cotton fabric. So this binder does not weaken the fabric but maintain the tensile strength. Also, the stiffness test shows that this BPW binder shows the stiffness value of 1.5 as compared to the synthetic binder, which says that for PC fabric, the binder provides softness to the fabric. However, in terms for the cotton fabric, results were slightly reverse. So, but it's still not very different. So we can believe that the results are comparable. We also tested the light fastness that the scale 8 says that there is no fading or no discoloration. And in the case, you can see here that once again, for this red pigment using PBW binder and the synthetic binder, there is no difference, and all of the materials shows the light fastness at the scale of 8. So this binder, imparts light fastness to the dyed fabric. So I would like to conclude that we developed a simple and fast and industrially adaptable procedures from banana pseudostem to develop a binder. And then these findings highlight the potential of waste utilization in creating sustainable solutions and minimizing the environmental damage. Our results were very good, and we can process it for the industrial processes. So I would like to thank you here once again. This is my address, and also I am on the list of mentors on African Academy of Sciences. So if anyone is interested, he can approach African Academy of Sciences to have me and a mentor, or for any research help that I can do. So thank you so much, and I'm open to questions.
Thank you. Thank you. That was really interesting. It was really interesting to learn from every context that was the subject of this presentation so far. And in the meantime, maybe there are some questions coming from the audience. I have actually a question for you all, for all the speakers, because one of my takeaways from your presentations, being not a technical, but also from other presentations during these 3 days, these other technical presentations, is that they emphasize the local resources and how they can be useful both for sustainable outcomes to reach the sustainable goals, but also to increase the potential of contextual technologies. So I was wondering, it's an open question to all of the speakers, so feel free to just jump in and answer if you would like, is what type of national support do you think is needed to increase the outcomes of this research, or the outcomes of cooperation of this support or on these researches, or maybe simply to increase the chance to deal with research with specific materials, from hydrogen, from fuels, from clean energies, or from specific chemical ingredients, as well as trees, as shown by Maria Thomas Costa. So how basically you envisage the role of national policies or international fundings or support for research in your own context and for your own research.
May I answer? All right. So in for my research or in context of Pakistan, we have two major issues, like establishing an industry, a local industry. Always, it requires some power. We need energy supply. So major issue of Pakistan is the energy supply. So energy is very, very costly. So if someone is establishing an industry, the product become very expensive. So if one of the thing is that there should be some mechanism to make the energy cheaper and are available at the cheaper rates to the local industry from the Pakistan government. And another thing is to create a market for the products. You see, if someone is producing in Africa, they are producing the hydrogen, but even if they produce the hydrogen, or I produce the products that are like the binders and things like that, so I'm a researcher, where should I sell this product? There should be and there should be the market, there should be the industry to take up this research and then produce at the mass scales, and then to create the market for those products. We need to create a supply chain that supports the local production of these kind of products that is coming from the local researchers.
Very clear. Thank you so much. I don't know if Mr. Oleka or Mrs. Maria, they have anything else to share?
Yes, hello. Regarding the national funding of policy as regards to Nigeria, one of the resources we have available here in abundance of its nature is solar. You can agree with me that in some developed countries, they lack this. And the good thing about solar is every other renewable resources in one way or the other have to do with solar. For example, wind is influenced by temperature change that generates it in some certain places, likewise thermal and all the rest of them. So it's a very good advantage in my own part. And at the same time, I will not stop appreciating the World Bank for the opportunity, especially as regards funding. At Futo, as I said earlier, the facility is a standard and international facility. The laboratory is there. The computational laboratory, which is the BioVia Material Studio Lab, is also there. We're furnished with the act-of-state equipment and facilities. All these things are there. But the challenge is that more fundings are still required. World Bank, I do not know how long they will be committed to this sponsorship. And it's at this point that we are calling upon some national policies that can encourage us and other intending students that intend to research more on this area for sponsorship. I think Nigeria have an energy transition plan, and all these things is moving towards using renewable resources in its energy sector. So if there could be more investment in this area, it will help us much more. Thank you.
Thank you so much, Mr. Odeka. And I welcome maybe all the speakers to give a final thought if they had one, since we have no further questions from the audience. I guess your presentations were really clear, and I would claim that. So if there's no final thought or answer to this question, maybe from Maria, then I would like to thank you all and possibly close this session. There's others coming. There's the final panel, the conclusionary panel today for these 3 days of conferences and technical sessions. So I welcome you all to follow the last ones and stay up tuned for receiving the recordings of these sessions and all the resources and materials, as well as for those that are in Rome, possibly joining the networking event. And I welcome also all the speakers to meet again, network, and share a bit more of these researches.
Thank you, Celeste, and goodbye.
Goodbye, everyone. Thanks, everyone, for participating.
Goodbye.